So we're going to talk about calorimetry, constant pressure calorimetry. So here we have what's called a coffee cup calorimeter. It's made of 2 coffee cups. With the top, we have a known amount of water in there, a thermometer, and a stirrer. So the heat of the system is equal to negative Sm delta T, where S is specific heat, mass, M is the mass, and of course delta T is the change in temperature. So Q of the system is equal to negative Q of the surroundings. Basically what that's saying is, if the system loses heat, the surroundings gain heat, and vice versa. The system gains heat, the surroundings lose heat. So Q of the surroundings is equal to Sm delta T. So how this works is, you do the reaction and you look at the temperature change. And if you know the amount of water in there, you can calculate how many calories are generated from the reaction. Okay, let's go over here. So here we have a metal pellet with a mass of 100 grams. So we have 100 grams, and usually I didn't bring a pen, so we're going to stop here for a minute. Okay. Once more. So we have a pellet, so it weighs 100 grams. It's at a temperature of 88.4 degrees Celsius. We put it into the calorimeter, which has 125 grams of water. And the raw water was originally at 25.1 degrees Celsius. Then we let it come to equilibrium. So the temperature, obviously, the pellet's going to lose heat, the water's going to gain heat. So when it stops, the temperature is 31.3 degrees C. So calculate the heat capacity in joules per degree C of the pellet. So the water absorbs energy, so we're going to use Q is equal to ms delta T. This little thing is this should be a delta sign, not a less than sign. We're going to convert it over to smartboard and change those. So that'll tell us the heat absorbed by the water. Well, what about the heat of the metal, the heat capacity of the metal? We can use Q is equal to C delta T, where C is the heat capacity of the metal. So there's the mass of the water. Specific heat of water in joules per gram per degree C. The temperature change was 6.2 degrees C. So the heat that's gained by the water has to equal negative Q of the pellet, the heat lost by the pellet. And negative means the heat's lost. The change in temperature of the pellet went from 88.4 to 31.3. So it's the final minus the initial. And this should be not 257, it should be negative 57.1, not 2. So change in temperature is negative 57.1. So to Q the water, we're going to use ms delta T. The mass is 125. Specific heat is 4.184 joules per gram per degree Celsius. 6.2 degrees Celsius energy change. So it's 3,242.6 joules. So that was the energy gained by the water. So the energy lost by the pellet has to be negative 3,242.6. So we plug that into the second equation, negative 3,242.6 joules is equal to the heat capacity of the pellet times the change in temperature, which was negative 57.1. So the heat capacity of the pellet is 57 joules per degree C. Now what they didn't show in this equation is from this, now you can calculate the specific heat of the pellet. Because remember, this is the heat capacity. The heat capacity is how much the object loses. How much did the object weigh? How much did the pellet weigh? 100 grams. So remember, specific heat is joules per gram per degree C. So if we divide that by 100 grams, we get the specific heat is 0.57 joules per gram per degree C. So if we had a bunch of different metals, somebody brought in an unknown metal, so I don't know if this is copper, brass, bronze, maybe all look the same. If you know the specific heat of all of those and you take a sample of this and run this experiment, you can calculate the specific heat and see which one it matches up with. So here's some heats of reactions. Some common reactions. So if we neutralize an acid and a base, top one, get a water and a salt, it gives off heat. Exothermic reaction. If you ionize water, to get water ionized, you have to add heat. If you look at the third one down, what are we doing in the third one? Melting the water. It's going from solid to liquid. So you would imagine, how do you melt water? You have to add heat. So it should be positive something. Oh, it's positive 6 kilojoules per mole. The next one down, what are we doing? What do we call liquid gas? Vaporization. Give me the common everyday term.
Boiling.
Boiling, thank you. Boiling water, 44 kilojoules per mole. So now I'm going to give you a choice. You can either stick your hand in a pot of water at 100 degrees Celsius or in steam at 100 degrees Celsius. Which one are you going to take? Why? Well, it's already at 100 degrees C. They're both at 100 degrees Celsius. Okay. Heat of reaction. So, remember I said if you go one way, you add heat. When you go the other way, you're going to release heat. Well, if you stick your hand in steam, the steam is going to condense. It's going to go from gas to a liquid on your arm. So it's going to release 44 kilojoules per mole onto your arm. Now you're going to have water at 100 degrees Celsius on your arm. So steam burned you twice. So steam burns are nasty. So if you've ever done what I do, you get home and you're hungry and you can't wait, you grab the little microwave thing and you throw it in there, microwave it for 30, 40 minutes or whatever it is on high. It's got that little film on the top, and you can't grab it, you try to rip it, it always stops when it just, and that steam comes pouring out. you get a nice little blister on your hand real fast. The steam burns really fast. So this is constant volume calorimetry. This is called a bomb calorimeter, and no, it doesn't explode. So this is an isolated system. Huge amount of insulation. So you have a known amount of water in there. And you have a sample container. You introduce oxygen, and there's an ignition source, and you burn the sample. So that heat's transferred to the water. And you have a thermometer in there, and you measure the temperature change. From that, you can calculate the calories or the energy in whatever sample you're heating. Since it's isolating, no energy leaves the system or enters it. So the change of the system overall is zero. So the heat of the calorimeter is equal to negative heat of the reaction. So we can look at the heat of the calorimeter is equal to C, the calorimeter, delta T, the heat capacity of the calorimeter. So the heat of the reaction is equal to negative the heat capacity of the calorimeter times the temperature change. So you measure the heat capacity of the calorimeter. So here we have good old famous Amos bite-sized cookies. They weigh 7.25 grams. So we burned one of these in a bomb calorimeter to determine its energy content. We had determined that the heat capacity of the calorimeter is 39.97 kilojoules per degree C. When we burn it, the temperature of the water increases by 3.9. So our delta T is 3.90 degrees C. Calculate the energy content in kilojoules per gram of cookie. So we're going to use Q reaction the RxN means is equal to negative C of the calorimeter times delta T. So calorimeter was 39.97. Delta T was 3.9. This is negative. So it comes out to be negative 1.559 times 10 squared kilojoules. So that's the heat released by the reaction. That's what the negative sign means. So they want the energy content per gram. Well, how many grams did we burn? 7.25. So that means each gram contains 21.5 kilojoules. So if we're going to convert that to calories, big calories, big C's, I go from kilojoules to kilocalories, or big C's, I divide by 4.184. Because 1 kilocalorie, or 1 nutritional calorie, is 4.184 kilojoules. So that's approximately 5 calories per gram. So the cookie was 7 grams. So each of those little famous Amos cookies is about 35, 40 calories. So if you're sitting there going, well, how bad can they be because they're only this big? You're watching TV and eat a whole bag of them. At 40 calories a piece, you can find out. And later this semester, when you do the experiment where we're going to calculate coating thicknesses using generic Oreos because I don't buy the real ones for you guys to play with. And the baking chocolate, and I'm going to calculate, you're going to have to calculate the new nutritional value of your new cookies. And that's the one time of the year where I let you guys eat what you make. And strangely enough, after you guys get done calculating how much the new cookies are, how many calories there are, nobody ever eats them. So everybody leaves and I have this big plate of cookies, which may explain a lot. Okay. Hess's law. I kind of like this. This is kind of fun. We said enthalpy was a state function, so it doesn't matter how you get from point A to point B. We're just interested in the initial and the final state. So when we do a reaction, it doesn't matter whether it's once, if I'm going from A to B, it doesn't matter if I do it in one step or 15 steps, I'm going to get the same answer. That's Hess's law. Okay? So if we look at these reactions, nitrogen monoxide plus ozone goes to nitrogen dioxide plus oxygen. The delta H is negative 198.9 kilojoules per mole. What kind of reaction is that? Exo or endo? Exo. Negative is exo. Ozone goes to 3/2 oxygen. Delta H is minus 142.3. Oxygen goes to 2 oxygen atoms. The delta H is plus 495 kilojoules per mole. Determine the enthalpy change for the reaction NO plus O goes to NO2. So here comes the fun part. And I really mean that because I think it's a lot of fun. We have to get these reactions in a form that they add up to the bottom one. The way I do this, I start with the first reactant, NO. Which of those equations has NO on the top? NO as a reactant. First. So I'm going to write that one down just like it is. I'm not going to write the states of matter because I'm lazy. And I'm going to put the delta H over here. Minus 198.9. And all of these are kilojoules per mole. What is the second thing in here? Oxygen atom. Do I have an oxygen atom? Here, right? The second equation, the bottom equation has an oxygen atom. But it's on the right. I want it on the left. How can I get it on the left? You're looking at the cap, right, of the pen. It's on the left. You want to see it on the right. What am I going to do? Same thing with the equation. How many oxygen atoms are in that equation? 2. But I only want to see 1. So what do? Divide by 2. So if I take that bottom equation, flip it, I get O goes to 1/2 O2. Now it was originally plus 495. So when I flip it, what's it become? Negative 495. but I only have half of it. So what do I gotta do for 495? Divide by 2. That's negative 2, 4, 7.5. Okay. Now I gotta end up with, I got the NO2, but wait a minute. I gotta get rid of, I gotta get rid of the O3, and I gotta get rid of some of the oxygen. So if I take the second equation, I want, since here I have the O3 on the left, to get rid of it, on the next equation I want the O3 on the right. So I'm going to take the second equation and flip it. And I have 3 halves oxygen goes to O3. Since I flipped it, that delta H is going to become positive, 142.3. Now if I look at these 3 equations, I add them up. Remember what we did with ionic equations to we cross-like things out? I can look, I had get rid of the O3, because that's on both sides. It's on the left here, it's on the right here, so I can get rid of those. Gotta keep the O, gotta keep the NO2. Oh, wait a minute. I got 3 halves there, 1 half there. One half O2, 3 halves O2. So there should be 1 O2. I'm missing an O2 somewhere. Oh, there was an O2 up here. There's the equation. So here I have 1 O2 plus a half O2, which is 3 halves O2. And these oxygens cancel out these oxygens. So I'm left with NO plus O goes to NO2, which is what I wanted. So to figure out the delta H of that reaction, I just add up these values, minus 198.9, minus 247.5, and 142.3. Everybody see what we did? Yes?
So we add the last one even though it's been canceled out?
Yeah, because it's still part of the total energy thing. And turns out to be negative 304 kilojoules per mole. That tells me if I react nitrogen monoxide with ozone to give me nitrogen dioxide plus oxygen, I'm going to liberate heat. It's going to be an exothermic reaction. These are kind of fun to do. And I'm going to pause here.